can you hear me? Hello?
Hi, Alex. Hi,
Can you hear
glad to
me?
see you here. Yeah, I can. Are you going to present your paper to replace Mattia?
I'm gonna try. I got like a half an hour notice, so I'll do my best.
Yeah, thank you for making this.
Sure.
Hello, everyone. Welcome to this software testing session. I'm the session chair. I'm Xiao, and Ji Yuan is a student volunteer in this session helping us. And today we will have 6 papers presentations, and the program runs like this: everyone give a 5-minute talk, and we save our questions after all the presentations. We will have an open discussion after all 6 paper presentations. And if you have any questions, just leave it in the chat box or raise your hand. And also, you can see in the chat box, Ji Yuan just shared a link to the program. You can go into the program to see the details of each paper and the information of the authors and so on and so forth. Any questions so far? Okay, otherwise we will get started. So the first paper would be the automated visual testing for mobile apps in an industrial setting, and De Zhiyan will be the presenter. Just go ahead to share your screen. Yeah.
Okay, can Hello everyone, I'm De Zhiyan from Peking University. I'm glad to present our software engineering in practice paper, automated visual testing for mobile apps in an industrial setting. Mobile apps has been an indispensable part of our daily life, and automated UI testing is a convenient way to assure their quality before they are shipped to users. Despite their usefulness, there are 2 main challenges handling automated UI testing for industrial apps. First, industrial app works on multiple platforms. Second, industrial apps frequently use non-standard UI elements, whose internal structures cannot be obtained by platform-dependent APIs. To address the preceding challenges, visual testing arises as a desirable solution. Visual testing identifies UI elements from screenshots instead of accessing platform-dependent APIs. Here is an example of visual testing in Sakuli, where widgets are represented as images. Using screenshots only, automated visual testing is applicable to any platform with no modification or little modification. In addition, automated visual testing is able to handle non-standard UI elements as long as the UI elements appear in the screenshots. To make automated visual testing a practical solution for industrial apps, we develop and deploy VTest. Due to time limit, we will only introduce the hardware infrastructure and UI element identification component. More details can be found in our paper. First, let's take a look at the hardware infrastructure. We use a high-speed camera to capture the image of device screens and a robotic arm with stylus pen to execute GUI events such as click or swipe on the device. Next, we select proper techniques to identify UI elements from screenshots. There are numerous UI element identification techniques falling into main categories. First, deep learning-based techniques use a data-driven approach. First, they are tuned on a set of training data, and then they are used to process the screenshots. While they are effective given enough training data, the data collection is costly when they are applied to a new app. Second, old-fashioned techniques use image grading to segment the image and locate UI elements in the screenshots. Old-fashioned techniques are data-free, but they may fail to handle complex UIs. We evaluate 3 deep learning techniques and 2 old-fashioned techniques on 5 scenarios on Taobao. Higher F1 score indicates better effectiveness. We found that old-fashioned technique, UIED, outperforms others in general with the highest average F1 score. In addition to the general effectiveness, when looking into individual scenarios, we found deep learning-based and old-fashioned techniques complement each other. Consequently, we can combine them to achieve best effectiveness at a low cost. Next, we evaluate the effectiveness of automated visual testing on Android in terms of activity coverage. Compared to Monkey, a state-of-the-practice testing tool for Android, VTest achieves 87% higher activity coverage with 90% fewer events, which demonstrates the effectiveness of automated visual testing. Then we examine the factor affecting the test effectiveness besides the identification accuracy of ULM elements. First, we find that runtime costs substantially affect the effectiveness. F-test and Y-test achieve similar activity coverage, although faster RCNN substantially outperforms YOLO in UI element identification accuracy. Fast RCNN processes a screenshot far slower than YOLO, bringing more runtime costs. Thus, we can improve the effectiveness of visual testing by reducing the runtime cost. Cache test caches and reuses the processing results of the same screenshot compared to U-test, which reduces the runtime costs of V-test and improves the test effectiveness. We deploy V-test internally at Alibaba Group and externally at Software Green Alliance China. V-test is used for both user experience testing and functionality testing. Here we list the most important lessons learned from our developing and deploying V-test. First, we should embrace non-deep learning techniques and their integration with deep learning ones to achieve the best effectiveness with low costs. Second, we should pay attention to improving the infrastructure support in addition to algorithm innovations. In this paper, we raise the awareness of the importance of visual testing. We propose V-test and design proper techniques to instantiate into a practical solution for industrial apps. We report our experiences and lessons learned. Thanks a lot.
Thank you. Okay, and our second paper is for Alex, the use of test doubles in Android testing.
Okay, you can see my screen, I think, and let me go in full screen mode.
Alex, you know it's a 5-minute talk, right?
Right.
Yeah,
okay.
I wanna say that because Alex is not the default presenter, and the presenter is actually sick. So Alex is doing our favor to present the paper. Thank you.
Right. Well, sure. And I'm presenting over PDF, so bear with me, please, because I don't have the same platform as Matthias. So this I'm really presenting on behalf of Matthias. So this is a work which is a collaboration between the University of Minnesota, India Software, and Georgia Tech. And the first author in particular is Matthias, who's a professor at the University of Minnesota. Okay, so first of all, I mean, I don't need to convince you that mobile apps are important. We use them every day, and we use them for a number of different purposes, reading the news, shopping online. And in fact, if you use applications, as most people do, you're just one of the 4.5 billion users. So there's a rich user population, and in particular, almost 72% of the users are actually using Android applications. So like any other application, mobile applications have bugs clearly, and like traditional software, one of the main ways in which people try to identify and eliminate these bugs is through testing. Okay, so the idea is that as you normally do in testing, you'll try to kind of find the issues in this way. There's something slightly different though about testing Android application, which is testing can be particularly challenging because Android application perform basically a large number of interactions, both within the application and outside the application. So there's a number of tightly connected components. And so tightly connected, basically part of the application, but also, and most importantly, a lot of interactions with the environment, and in particular your interactions with the network, interactions with sensors, cameras, GPSs, microphones, and this is kind of peculiar to the Android application. So because of this number of interactions, there's a number of issues that might occur. So one in particular is that the problem of flaky test is particularly relevant for mobile applications. And let me actually remove this so you can focus more on this. So the number of flaky tests that can be higher because of these interactions that might cause non-deterministic behavior. The interaction could also slow down the test. In particular, if you have to have a lot of interactions with the environment, testing can be more costly. And also there's interference bugs due to dependencies within this application. And so one possible way in which you can address these issues is through the use of test doubles. So for example, if you have an interaction with an external network, what you can do is you replace the external network with a test double, basically something that replaces the external systems. And sometimes these are referred to as mocks or with other terms or stubs. But in this presentation and also in the paper, we use the term test doubles because in this way we avoid confusion. So that's sort of the generic term that includes the test doubles, mocks, and so on. And so there's two main ways in which test doubles can be used. One is to provide specific outputs given an input, so replacing an external component. Another way in which they can use is to test the interactions with the external component. For example, to make sure that some calls are performed or that some calls are performed with the right sequence. And despite the fact that test doubles can be very useful in the context of Android, there's not any really specific study about the use of test doubles in Android. There are some studies about Java, but there are some peculiarities about the Android ecosystem that makes it so that we really wanted to kind of get a better understanding of how they're used, because we're interested in kind of supporting developers in the use of test doubles. So what we did, we performed an extensive study in which we investigated a number of research questions. In particular, we looked at which frameworks are the most used, what type of classes are replaced with test doubles, what type of test doubles are created, how tests interact with these test doubles, and also, finally, what kind of problems can be introduced by the use of test doubles. So in order to do this, we performed a kind of a study in two parts. The first part was a part with a very extensive data set of over 1,000 applications. And we used this study in order to figure out which frameworks and approaches are the most commonly used in order to create test doubles. And in the second part of the study, we basically extracted 10 applications, and we performed a more focused investigation. The reason why I found these 10 applications is because this is a very thorough kind of examination, and therefore required also a lot of manual work. And so doing it with a larger number was problematic. But on the other hand, what we did, we tried to select a representative subset of the applications in order to do the second part. So I'm not going to have time to discuss, obviously, the results and all the details. So what I'm going to do is just going to give you a high-level overview of the actionable insights that came out from this study. So first of all, the importance of test doubles in Android testing. So our studies show that there is a considerable percentage of apps that contains automated tests that also use test doubles. So it makes sense to develop techniques that help developers in this context. We also found out which ones are the most commonly used frameworks, which are Mockito and Mockito Kotlin. So if you want to develop a tool for this kind of task, you might want to target these applications. We also saw that there was a need for techniques that support creating and maintaining test doubles. And if there is this need, they should focus on two main kinds: stubs, so helping developers identify which methods require stubbing, which methods require to be replaced, and also mocks, basically helping the techniques that will help developers decide which interactions to verify. Finally, we saw that there's an opportunity to automatically identify which classes will be replaced by with test doubles. In particular, we saw that configuration and GUI components are very often part of the Android framework or inherit from class they're in, and they can be easily identified and proposed as possible candidates. And really, finally, we found out that there's also some specific issues that might occur with the use of test doubles, and in particular, we identified some sort of test smells that are related to the use of test doubles. And so another possible venue for research will be to identify techniques that can spot these problems. That's all I have, and I just want to point you to the artifact. We have an artifact for this, so if you're interested in the details, look at the paper, or you can look at the artifact.
Thank you, Alex. And okay, our next paper is inference and test generation using program invariants in chemical reaction networks. And Michael Jerton will. Michael, go ahead, share your screen.
Awesome. Hello, I'm Michael Gerton, and I'm presenting inference and test generation using program invariants in chemical reaction networks. Molecular programming is an emerging computing paradigm. Some of the technologies we can implement include logical circuits, neural networks, and molecular robots. These can be used to create technologies such as intelligent drug delivery and other nanoscale technologies. In order to implement these molecular programs, we start with the functional behavior we want to represent, which can then be compiled into DNA in a solution, thus creating a physical output. However, we still need to know that these programs are correct, and it's often infeasible to check these programs in vitro, so we want to be able to check them at the simulation level. Current state-of-the-art, however, requires us to create manual specifications in order to evaluate these programs. Often, molecular programs are represented as chemical reaction networks. Here's a function of the parity, which takes an input x and returns whether or not it is even or odd as a Boolean result. And here is it implemented as a CRN, which has 4 reactions and 4 species, with x as the input species and PE and PO as the output species. If we wanted to represent this program in a specification, though, we need to think about how its behavior is. The first one I can think of is that if x is odd, we expect PO to be true. To write this as a specification, we borrow techniques from linear temporal logic in order to show this specification holds at all times in the simulation after we evaluate it. We can also write specifications using metamorphic relations that involve multiple simulations of the model. And as we move to more complex models, our specifications can include things such as probabilistic bounds on the properties we want to evaluate. Given an arbitrary CRN here, even if the functional behavior is relatively simple, writing a complete set of specifications that capture the program's behavior can be difficult and time-consuming. So we asked, is there a way to infer the specifications for the CRNs? Borrowing techniques from Petri nets, since it has been shown that stochastic chemical reaction networks are equivalent to an implementation of Petri nets, we were able to use linear invariants or p-flows in order to infer specifications from the models themselves. In this work, we present ChemFlow, which is an invariant inference tool that is able to be used for model comparison and test generation. ChemFlow works by first generating invariants from the model, which create 3 types of invariants. The first type, flows, uses species counts in order to evaluate and are the simplest. The second type, inequalities, uses both species counts and reaction counts, but removes the reaction counts in order to be evaluated more simply, but reduces its oracle power. And the last type, irreducibles, uses both species counts and reaction counting, but requires a different additional scaffolding to be evaluated, and thus is most costly. However, it does add additional coverage that the other invariants do not offer. We can then use these invariants for model comparison in order to check how these CRN models are holding up, as well as evaluating abstract test suites that can be implemented into the current state-of-the-art testing framework for chemical reaction networks, ChemTest, allowing us to check the quality and faultiness of these models. In order to evaluate CRNs, we use 13 subjects in our case study, 9 of which we were able to generate manual specifications, and 4 of which we are not able to create a set of manual specifications, including natural programs such as an E. coli organism model with nearly 500 species and reactions. When we check the fault detection of these models, looking at the 9 which we were able to generate manual specifications, we saw that the flows did have a good fault detection ability, but when we used all 3 types of invariants together, we saw fault detection on par with the manually generated specifications from ChemTest. We saw a similar level of fault detection using the invariants in the 4 models without manual specifications as well. When we looked at model comparison, looking back to the E. coli organism from before, when we generated the invariants on that model, we found certain islands of behavior that were disconnected from the larger model. When we asked developers about this behavior, they said it was indicative of possible model quality issues, as the behavior should have been interconnected with the larger model. They have since asked us to look at other biological and natural models in order to investigate similar model quality issues. In summary, we have presented ChemFlow, an invariant inference generation tool that allows us to do fault detection on chemical reaction networks and investigate model quality issues in natural molecular programs. We do have artifacts available online, and thank you.
Thank you, Michael. Okay. Paper is called controlled concurrency testing or periodical scheduling, and Chen Wen will present that paper. Feel free to share your paper. Yeah.
Okay, good.
Go ahead.
Hi everyone, my name is Chen Wen. I'm going to talk about controlled concurrency testing via periodical scheduling. Controlled concurrency testing is a technique for testing concurrent programs. It controls the order in which threads get executed and explore the space of possible interleaving to detect bugs. There is a good number of existing work. They can be divided into systematic testing and non-systematic testing. Despite of their researches, limitations and challenges remains for state-of-the-art controlled concurrency testing technique in terms of control scheduling and schedule space exploration. Many different ways to achieve control scheduling are used in existing work. Some approaches require serializing a concurrent program or injecting sleeping delay to interfere with the thread interleaving. They will introduce high overhead, making fewer interleaving that can be tested in a limited time. And real-world programs use a plethora of synchronization primitives. The preempted way could have pathological interaction with the synchronization operation in the target program, leading to false deadlock. The challenges is how to achieve better control scheduling. Another aspect is about schedule space exploration. Exhaustively enumerating all possible thread interleaving is often practically infeasible. The number of thread interleaving grows exponentially with the number of threads and the length of program execution. Randomized technique only provide probability guarantee of finding bugs. Systematic technique tend to go through a large schedule space than needed, requiring more overhead or missing some bugs. Thus, the challenges is how to effectively explore the schedule space. To address the aforementioned challenges, we propose a novel systematic controlled concurrency testing technique called PERIOD. It achieves better control scheduling in an efficient and non-preempted way, and it achieves more effective schedule exploration by using 4 key techniques. Let's take a quick look at the workflow of PERIOD, which contains 3 main components: schedule generator, periodical executor, and feedback analyzer. Given the source code of the program, PERIOD first applies static analysis to identify key points. Key points are the statements that are key to the program observable behavior, such as the statement assessing shared memory location or synchronization primitives. The schedule generator generates schedule according to the number of key points. A schedule is a series of execution phases that contains thread identifier. The schedule generator employs a schedule bounding technique to systematically generate schedules that are likely to induce bugs. The periodical executor uses a series of periods to host the execution. It enforces the generated schedule in the execution. The feedback analyzer makes use of runtime information such as key points, dynamic key point slice, and schedule prefix to guide the schedule generator to effectively generate legal schedule. We also design a parascheduler. The parascheduler allows the isolation of specific order on field segment while letting the rest of the program execute concurrently. This optimization makes it possible to reduce the schedule space to explore. We have implemented our approach in a tool and performed a thorough evaluation. For comparison, we have selected 6 well-known and representative controlled concurrency testing techniques, 2 recent work that use predictive analysis, and also 3 race detectors. The results show that PERIOD successfully identify more bugs than other competitors. We also include both versions of Period equipped with our Period scheduler and without the Period scheduler. With Period scheduler, Period explore more schedule space effectively, allowing more bugs to be detected. The result also show that both versions of Period outperform other controlled concurrency testing technique in terms of concurrency bug finding ability. In summary, we present a controlled concurrency testing technique. It achieves better control scheduling and more effective schedule space exploration. It outperforms the state-of-the-art controlled concurrency testing technique, and you can try our artifact out from this link. And at this point, we were happy to take any question. Thank you.
Thank you. Okay, and the next paper is the SIM tuner. Okay, this is a distinguished paper. Congratulations. And Mi Man Ho is going to present their distinguished paper.
Okay, thank you. And can you see my screen?
Yeah.
Okay. Okay. Hello, everyone. Oh, sorry. Hello, everyone. I'm Myung-ho Lee from Korea University, and I'm glad to have a chance to present our work SIM tuner today. The goal of this work is to automatically tune the many parameters of a symbolic execution via online learning. This is a joint work with Soo-young Cha from Sungkyun University, Seok-hyun Lee, and Hak-jo from Korea University. And let's start with the motivation of our work. So as you know, symbolic execution is a powerful white box testing technique. At a high level, symbolic execution takes a program as input and aims to automatically generate the test cases that are likely to trigger the program crash or increase the code coverage effectively. And because of this well-known performance and effectiveness, many symbolic execution tools such as CLI and SAGE are actively used in both academia and industry nowadays. But in reality, using these tools effectively is not simple. When we try to use these practical symbolic execution tools, there is an essential process we have to check first, which is a process to determine the diverse parameter values of the symbolic execution. In this work, we define these parameters as the factors that critically affect the effectiveness of a symbolic execution, and hence, proper parameter tuning process is important to achieve high code coverage and find many bugs. And however, the problem is that there exist numerous parameters of practical symbolic execution tools. This figure shows the typical parameter setting of the symbolic execution tool CLI. As you can see, there are many specific parameter values for symbolic execution, such as max memory, which limits the memory usage, and SIM ARGS, which specifies the number of symbolic arguments to use. As there are numerous parameter values and options, like manually tuning such parameters becomes a natural challenge, which is difficult not only for end users, but even for the domain experts. It will be a challenging task to determine appropriate values for all these question marks that consist of diverse types. They can be the Boolean type, integer types, or any like the string types. And now you may wonder how the previous works handled this challenging problem. Okay, let's see how they did. The prior works developed on top of CLI usually use the default values or the hand-tuned values provided by the original authors of CLI without any modification. And you can see the later sentences. And otherwise, only some specific parameter values are manually adjusted for each target program to get the maximized performance. Like for example, the parameter SIM ARGS is manually adjusted for each target program differently, like the 0310 for DD program, and like 04300 for echo. And as you can easily imagine, manually tuning these parameter values for each target program is really time-consuming and labor-intensive. And that is our motivation of this work. So our goal is to automatically tune these kind of many parameter values for each target program during symbolic execution to maximize its performance. So our technique SIM tuner takes as an input symbolic execution tool, any kind of symbolic execution tool like CLI, a target program, and the parameter spaces we want to tune. So for example, let's say we want to tune 4 parameters: the memory, max time, search, and SIM ARG. Taking these inputs, SIM tuner iteratively samples the parameter values from the predefined spaces, then performs a symbolic execution with these sampled values like the ones on the right. By observing the feedbacks from the performing these executions, SimTuner learns like which parameter values would be likely to maximize the performance of symbolic execution. And to achieve this, the key idea of our work is a customized algorithms for effectively learning the sampling probability of each parameter spaces during symbolic execution. So as a result, over all 12 open source C programs, of which sizes ranges from like 5,000 to 161,000, SimTuner consistently achieved 31% and 56% higher branch coverage than the two baselines without parameter tuning. And the two baselines are the like CLI with hand-tuned parameters, the one I showed at the beginning of the talk, and the CLI with default settings. Moreover, SimTuner was able to find 11 different bugs in the latest versions of 4 open source C programs. These results show that SimTuner, our work, succeeded in significantly improving the performance of symbolic execution in terms of both branch coverage and bug finding capability, even for the real-world programs. So in summary, to best our knowledge, SimTuner is the first work which tackles the importance of a parameter tuning problem in symbolic execution and automatically tunes the parameter values of symbolic execution via line learning. And we make our tool SimTuner publicly available. You can easily git clone our work through the link. We hope that SimTuner can help end users to gain maximized benefits from powerful but difficult to use modern symbolic execution tools. And that's all for my talk. Thank you for listening.
Thank you. Okay, and now goes for the next paper, the path transitions tell more. The presenter would be Kunpeng Zhang.
Hi, my name is Zhang Kunpeng. I'm going to present path transitions theorem, optimizing fuzzing schedules via one-time program states. Fuzzing is a widely used tool to exploit security issues in software. Existing solutions to improve the efficiency are twofold. The first category intends to reduce the space of inputs, and another category is to optimize path schedules. For the first category, the existing solution to reduce the input space is to infer the relationships between the input bytes and the path constraints, which improves the efficiency of resolving path constraints. However, a real-world program could be far more complicated, as the byte constraint relation could exist between multi-byte and multi-different constraints, or even nested. As the inference relies on the changes of execution states, the changes can be explicitly and implicitly influenced by the mutation of certain bytes. Thus, when the inference process intends to infer the relative bytes for the inner condition in a nested condition, the result may enormously include the bytes related to the outer condition. As a result, when fuzzing tends to resolve the inner condition, fuzzing may mutate the relative bytes of outer condition, which will alter the branch of outer condition. To avoid this problem, we observe the difference between two execution paths of a path transition imply properties of programs. Specifically, the paths that examine the error handling code are usually much shorter than the paths that examine functional code. Based on this observation, if the mutation of certain bytes results in significantly shorter paths, these bytes are likely related to a validation check. Then we can identify these bytes related to the validation checks, protect those bytes from being frequently mutated, making most generated inputs examine the functionalities of programs instead of being rejected by the validation checks. In order to determine such a relationship, Trust computes a fitness for each byte by mutating it and observing the difference in a path transition, measuring how likely a byte is related to a validation check. Based on the fitness score, Trust then assigns lower mutation possibility to the validation-related bytes, protecting them from being mutated. The difference in a path transition can also optimize the seed prioritization. If a seed transition discovers a path that includes many new edges, it's likely to explore an undiscovered code region. More new edges covered in a path may lead us to more undiscovered descendants, as it may have touched many more new code regions, so that we should focus on such seeds that discover more new edges until they have been tested. In order to prioritize seeds, Trust ranks each seed based on the number of newly discovered edges when a seed is first returned. To To evaluate our charts, we implement charts with 6 phases and compare the performance with the corresponding vanilla phases. First, we want to figure out how effective is byte analysis to guide more generated inputs flow into functional code. As shown in the figure, under the same conditions, a charts-equipped phaser can generate more valid inputs than the vanilla phasers. Second, we run 2 versions of phasers on A programs for 24 hours and compare the average performance with respect to edge coverage. Charts-equipped phasers discover more new code coverage than the vanilla phaser. Third, we compare 2 version phasers in terms of the number of real-world bugs. In total, vanilla phaser and charts-equipped phaser find 10 and 13 bugs respectively. Finally, we summarize our work. First, we propose a lightweight framework charts to improve the performance of CGFs. Second, we evaluate charts with respect to valid input generation. Third, we implement charts with 6 phaser and compare the performance with the vanilla phasers. That's all. Thank you.
Thank you. Thanks for all the great presentations. And now we have 25 minutes left for the open discussion. And anyone, including the presenter, you can ask questions to any presentations.
Here, I'll get us started. I had a question for Alex.
Okay.
With the test doubles, so I understand kind of that they're being used to kind of remove some of the errors that we're finding in these programs based on the interactions with like the system. But aren't some of those faults things we want to be able to evaluate? Because if the program's failing because of some Android interaction, maybe that's something that we need to address. How does that kind of fit into your work?
Right. Yeah, no, so it's a good question. So yeah, basically, typically the doubles are not really used to eliminate errors, but more for eliminating issues that make the tests either less reliable or less efficient, let's say. So for instance, imagine that you're interacting with the network. It is true that you might want to know if the network fails, what happens to your program, but to some extent what you're testing, I mean, you know that the internet connection can drop at some point, right? So the test is not really testing the network. The test is testing the application that interacts with the network. So in order to test the functionality, you want to make sure that whatever the environment is supposed to do, it does. And then you can have some robustness testing, maybe that you will do without doubles, in which you want to see how often the network goes down or similar situation. Another example would be, imagine that you interact with a large database and you have to start the database populated, and that can take just a long time in order just to set up the test. So in that case, you will use the test double in order to completely eliminate that part, and so to be very efficient. In fact, something that we found out, for example, is the fact that test doubles, unsurprisingly, are used much more often for JUnit tests. And so for basically local tests. So you will use the test doubles in order to test the functionality without having to worry about the environment. And then you might have system tests that will identify the kind of errors that you mentioned.
Awesome. Thank you.
If that makes sense.
Hi, Alex. I have another question about the test doubles. Is it possible to automatically generate the TDs if they share some common characteristics for different projects?
Yeah, that's what we want to do. So our goal is really to try to support the sort of automatic or semi-automatic generation. And so some of the things that we found, for example, I had it in one of the slides about the findings is that there are some specific kinds of classes, for example, that tend to be replaced with test doubles. So a first possible way to do that will be, yes, it is doable, and you could basically do some analysis and perform if you identify these kind of classes. So typical example could be a class that reads some sensors. So you can generate a skeleton for that, and you can also do it by, for example, recording and replaying, or just by generating the frame for the double and then proposing it to the developer. So I guess the short answer is yes, for at least some cases. And then there might be some test doubles that instead are very complicated because they test the interactions between, you know, 3 different kind of classes. And maybe for those ones, those are the ones that will have to be computed manually. But we feel like based on our findings that there's at least some that can be automated or, you know, at least, you know, kind of highly automated, if not fully.
Okay, thanks. Thanks for your answer.
So thanks for the question.
Hi, Chen. Here is a question from Myra in the chat box. Can you see that?
Yeah, I can see the question.
Okay.
The question is, can you explain a bit on how the scheduler works for the schedule, the thread ordering? Okay, the scheduler try to systematically explore all the thread interleaving, but in some limited rules. For example, the scheduler only explore the schedule interleaving that the context switches is less than a bound. On the other hand, the scheduler not explore the schedule space on all the segments of the concurrent program. First, it only run many segments. After finding other segments, the thread order will contain the other segments. So the scheduler is explore the schedule space gradually. That's my answer. Good for you.
So so it sounds like you're using different heuristics and rules to do that.
Yes.
That helps.
Thank you. Any other question?
For Young Ho. So I'm just curious about how, you know, the sampling probability. So it wasn't clear to me where the probability is coming from. Is this the history? So do you have a corpus of programs that you're using, or are you doing, you said you're doing online learning, so you're learning as the programs are running. Maybe you can explain a little bit. So if I have a new program that I want to use your AutoTuner for, is it going to use history, or is it going to do this learn as it goes?
Oh, we learn the probability as it goes. Like by online learning, we didn't use any. We didn't do the offline learning, but we collect the data from like during the like simple execution process, and using the data, we learn the probability ongoing. Is that the answer for your question?
Just trying to understand.
Okay, thank you.
And
Can I ask
Mary,
you
have another question? Okay,
Yeah.
go ahead.
So I just want to follow up on that. So, you know, how long does it take to tune that? I'm just curious. So again, it's online. So is there overhead on using the tuner if I'm trying to, sometimes something like Klee can take a while to run. Did you look at the overhead for that, or is it pretty much doing it with little overhead? What's the sort of cost of it?
Well, the overhead is like negligible. It's very small. It's very low. Like, yeah, it doesn't take that too much time on like tuning or something like that. Okay.
Yeah, actually, I have a question here because I think for all the presentations, I think some of papers you pick up like a more black box testing. I mean, I have a general question for all of you, yeah, because so it's a more black box for like for Android apps or mobile apps. I think those the first 2 papers, right? The way you're testing and Alex paper is all about testing of the mobile apps. I think it's more black box testing, and the other two by Minho and Kunpeng Zhang, it's more at the code level. It's white box and gray box, right? So, so I'm curious. So is there this white box and gray box tool at the code level testing apply can be applied to the Android or the mobile apps at the code level? It's like what kind of platforms? It's only applicable to desktop, or it's also widely used in the mobile apps world. It's I'm curious to. Does that make sense? So I'm curious to know more a code level testing and in the mobile apps world testing. Any?
Well, it's just my opinion.
Mm-hmm.
But I think we can apply the white box testing to the mobile applications if they provide the code and the simulation settings that we can simulate the program behaviors.
Yeah, and I think and I know Kali is a C program only, right? It supports other programming language. Kali.
Yeah, it basically only provides for basically it's only for the C programs, but you can just
okay.
But there are a lot of the variants that targeting the other types of programs such as Java or the other language.
Okay. You mean the other symbolic execution tools working with other programming languages, right?
Yeah, you're right. You're right.
Any other questions?
So I can.
Okay, so
last paper. Like on your last slide, it looked like you used about 6 or 7 different fuzzers, so I couldn't get everything. It was too fast. So I saw AFL and I saw 3 or 4 other fuzzers, and it looked like your coverage. But can you give me a little more detail of what was the sort of magnitude, or I saw the graphs, but obviously in 5 minutes I can't really. I couldn't get a good sense of how much more coverage, and maybe you can just give us a little more detail on that. So I got some percentages, but was it 50 more paths in a program that has thousands of paths, or was it just a couple more? So maybe you can say a little more.
Could you please repeat the question?
In that last slide, you showed about 5 or 6 different fuzzers that you compared against, and you found that you had better coverage, you had better path coverage. And I'm trying to get a sense of what the actual magnitude of that improved coverage was. Was it 2 more paths? Was it hundreds of paths more? Just maybe you can, and how did that relate to the time of the fuzzers, right? Because in a large program, did you just get 1 new path, which might be good, or did you get 20 or 30 new paths?
Oh, let me think about it.
Maybe you can share a screen to go to point to the slide, the result slide, and to expand a little bit more. That might be easier for you to answer this question. Yeah.
Wait a minute.
Yeah, I think you have one slide showing all the comparison of coverage.
implement this feature.
So it's hard for me to tell, I see that it's improved coverage, but where does it look, or this, can you give me the magnitude of how much better it is?
On average, 20%, roughly 20% improvement. I'm mainly in the paper.
Okay, so 20%, and these are not small programs. Okay, thank you.
Hey, Chen.
Go
I
ahead.
was wondering, when you are choosing the key points to kind of have the scheduler kind of choose, is it a manual process, or is there some way? Is it automated in some way to kind of split up the program?
Okay, the question is about the key point. We apply the static analysis to identify the key point. The key point is the statement that a shared memory location or some synchronization primitives such as lock, unlock, or wait signal. In our implementation, we use a pointer analysis technique to identify whether a variable is point to a shared memory location. That's my answer. Good for you.
Yeah, thank you.
And I have another question for Dezhi. Yeah. So for this automated visual testing tool, so I'm curious to know what the biggest challenging, like when you implement the tool and apply it to the real industrial settings. So
That's
the
for
presentation was,
question.
yeah. I'm sorry. Did you get my
That's
question?
for a question.
Okay,
Yes,
go ahead.
Thanks for a question. It's a good question. I think the biggest challenge is to balance the costs and the effectiveness of the tool implementation. As I discussed in my presentation of the UI element identification parts, we use a hybrid approach, combining the old-fashioned computer vision techniques and the deep learning-based techniques. The main motivation of our selection is the cost, because if we can collect large corpus of training data, UI screenshots, we can simply use the deep learning techniques to obtain a good trained model to identify UI elements from the screenshots. But in practice, we do not want to collect such a corpus of training data because it's costly. And the app evolves, which means the data used previously may not reflect the current app. So the trained data we should add more data and retrain the model, which is not acceptable for industrial use. So we basically use old-fashioned techniques, which do not need data to fine-tune them. So it is cost-effective. And we just use the deep learning techniques to identify the UI elements and the old-fashioned techniques cannot handle, which requires far fewer trained data, and to achieve a good balance between the cost and the effectiveness.
Okay, thank you. And for different apps and environments, they choose a different balance, right? According to different requirements and different types of the environment, right? It's not
Yes,
fixed.
exactly.
It's not okay.
for you. So you sort of mentioned just slightly at one point about some aspect where some of the doubles were related to configurations or parameters. Can you maybe say a bit more about that? I don't know if you remember where you said that, but right in one slide, you just sort of mentioned it very briefly. And I was curious if you had more detail on, are those including or, yeah, I mean.
Yeah, so basically that's one of the things that we found that was very different from the results from other studies that were not for Android application, but for Java application, which I guess it has to do with the fact that maybe Android applications are specific, have probably more configuration or more parameters, and also GUI elements. So basically we found two very frequent parts of the application were replaced were the configurations, so the reading of configurations parameters, and also the interaction with the GUI. And so that's and it's something that was not reported in other studies on Java. And so that's something that sort of will justify the fact that that there are some specificity to the depending on the domain, and also provide some guidance on where you might want to help developers. Does that make sense? It was basically those were the Android specific test doubles that we found: configuration and GUI component classes.
Okay.
And it's just see, there's another question. Just letting me add to that. So that was also one place. I think there was a question before from Desi about the where you could help developer automatically. So in this case, it's very easy to identify configuration and GUI component classes because they're either part of the framework or inherited from that. And so that will be one first place. Like for example, if you want to kind of get a low-hanging fruit, where you might want to go and try to generate test doubles automatically.
Thank you.
Thank you. Any other questions? Okay, I think we're good to wrapping up the session. Thank you everyone for attending, and thank you for our great presentations. Okay. And if you have any other follow-up questions, you guys can chat in the coffee room or break room virtually. Yeah. Okay. Thank you.
Thanks,
Bye.
Ciao. Bye.
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 Bye.